All right, for the second part of proving Green's theorem, we need to do the other side of Green's theorem. Last time we showed that the line integral was equal to 1/30th. Now we want to show that the double integral over the region of the partial of n with respect to x minus the partial of n with respect to y, dA, also equals to 1/30th. So let's take a look at our picture that we had here last time. We know we were coming up the curve that way and back down that way. So the bounded region here is the region that we want to integrate across. So that's our region R. So how are we going to set this up? So dA, since we're in the xy plane, is going to be dx dy or dy dx. Since we know what these functions are in terms of y, the bottom one is y is equal to x squared, and kind of the top one over here is y is equal to x. It would probably be smarter to do the y direction first than the x direction. So let's start by setting this up. The partial of n. Well, remember this is m dx plus n dy. So grab a pen. I have a red one out. So I'm just going to do it up here. So remember this is our m dx plus n dy. So according to this, I need to take the derivative of n with respect to x. That's going to give me a 2x minus, then I take the derivative of m with respect to y. That's going to give me 2y. And then, of course, we're going to integrate this across our region dA. All right, so let's see if we can integrate this across our region. Let's go dy dx. We said that would be easiest. In this region, y goes from y equals x squared to y equals x. So this goes from x squared to x. Now once we integrate out the y's, this drops down to just the x direction. You can see x goes from 0 to 1. All right, so let's start integrating. When we integrate with respect to y first, this gives me 2xy minus y squared, and we need to evaluate that from x squared to x dx. Like top endpoint, so when we plug in the x, I get 2x squared minus x squared minus bottom endpoint, that's going to be 2x cubed minus x squared. Squared would be x to the 4th dx. All right, let's combine some like terms here. So this just gives me x squared minus 2x cubed plus x to the 4th dx. All right, integrating each one of these, that gives me 1/3 x cubed minus 1/2 x to the 4th plus 1/5 x to the 5th, evaluated from 0 to 1. And to integrate that right, 1/3, 1/2. All right, so top endpoint, that gives me 1/3 minus 1/2 plus 1/5 minus 0. And we plug in 0, we get 0 for all those. So a common denominator there is 30. So that's going to be 10 30ths, 15 30ths, and what's that going to be? 6 30ths. So 1/30th. All right, now notice that matches our result from the first side of this integration. So the idea here is, with this theorem, you have options on how to handle a line integral like this. If it's very, very hard to set up a parameterization for this, it may be easier to do this integral just integrating across the area. Or the other way around, if it's a very, very complicated area, it might actually be easier to do a couple of separate line integrals to come up with the same answer. So this just gives you options on how to evaluate these things. Now there's another result that we can get from this. And we're going to do just a little bit of notation that's not in this textbook that we're using, but a lot of textbooks do use this. For Green's theorem, we said that this had to be a simply closed curve. Now the way that you'll see this, let's just say m dx plus n dy. The way that we sometimes show a closed curve is on the integral bar. You might see a circle drawn right there. That means that the region that you're talking about, in this case a curve, is closed. Is equal to, and of course this is the double integral over the region, partial n with respect to x minus partial m with respect to y dA. So there's what Green's theorem says. Now again, We could do the closed circle on this side as well. Now you do it across both of them because the region that we're talking about is a closed region. If you see these circles around integrals, that means whatever you're talking about is enclosed. Now we saw from a couple of sections ago that if we integrated in a conservative field and the curve was closed, went all the way back around. If f was conservative, then we knew the integral of f dot dr around c was 0. Remember, this is just the differential form of f dot dr. Now you can see that this also shows that it's true. For a vector field to be conservative, right, if this was our vector field, the partial of m with respect to y has to be equal to the partial of n with respect to x. Or, if you subtract the two, that would be 0. So you can see if this m and n gives us our conservative vector field, this has to be 0, which means that line integral has to be 0. So it's just another way to prove that if you're integrating in a conservative vector field on a closed curve, the answer has to be 0. And you can see it from this side. Or another way to think about it, this is the kth component of the curl of that field. So very, very interesting result. Green's theorem can be very helpful when evaluating line integrals and area integrals.